Physics 2212, Lab 6, Faraday's Law. The goal of this lab was to collect observational data of a magnet falling through a conductive tube of aluminum foil, model the magnet-tube interaction computationally using GlowScript, and comparing our computational predictions to our observed data. The purpose of this lab was to overall explore the applications of Faraday's Law through a common phenomenon. Some key concepts involved in this lab is Faraday's Law, which relates the electric field to a magnetic flux, which is equal to the line integral of the dot product of the electric field and the change in length of a path, and this is equal to the negative derivative of the magnetic flux. And magnetic flux is equal to the integral of the dot product between the magnetic field and the change in area, or more commonly as the product of the magnetic field and the area. We are also given an equation for the change in magnetic flux, which is given below, and the electric field E produced by the change in magnetic flux follows the loop in the same direction as the current I. Another key concept is the magnetic force on a wire loop, which is equivalent to the cross product of the length vector and the magnetic field vector multiplied by the current I, where L points in the direction of the current and magnitude equal to the length. On a loop, we have that the magnetic force on the wire loop is equivalent to the equation below. Another key concept involved was Newton's third law, which is important because we note that the magnitude of the magnetic force on the loop is equal and opposite to the force on the magnet by the loop. And Ohm's law allows us to calculate the current from the potential difference and the resistance, where current is equal to the potential difference divided by resistance. And the potential difference is also the induced electromotive force, which is equal to the negative derivative of the magnetic flux. The procedure for this lab was to first we mark the north pole of the magnet, and we measured the mass of the magnet. Then we measured the following three attributes of the aluminum tube, including the width of the foil, the inner radius of the tube, and the length of the tube. Then we dropped the magnet through the aluminum foil tube 5 times and determined the time that the magnet takes from entering the tube to exiting the tube each trial. Finally, using GlowScript, we created a computational model of the magnet aluminum tube interactions using the dipole moment that we had from Lab 3. We then compared our observational results with the computational results in this lab. The results are shown as follows, where we had an average time of 1.21 seconds for the magnet to enter the tube and exit the tube. The length of the tube was 0.46 meters, with a width of the aluminum foil of 0.101 meters, and the inner radius of the tube was measured to be around 4 centimeters. The mass of the magnet overall was 0.02 kilograms. Hence, by adding the width of the aluminum foil and the inner radius, we get that the total radius was around 0.05 meters. And from our previous lab, we calculated that the magnetic dipole moment was around 1.496 am squared. Here is the link to our computational model for this lab. Pay attention to the definition of constants, the magnetic field, and the flux function, as well as the simulation loop. Here we see that we define our constants first, with μ0/4pi resistivity and g, and we set up various initial conditions such as the length of the tube and the radiuses, and we have other sections that create the bar magnet and set up an initial loop, and we create functions to calculate the dipole, the magnetic field of the bar magnet from mu, and then we also have a function to calculate that magnetic flux from the same thing. We finally have the simulation loop where we motion prediction and visualization, and through all these commands we get this final product when I've run this program. Overall results were that the simulation predicted that the magnet would take 0.284 seconds as opposed to our observed times of at least 1 second. This means that increasing the dipole magnetic moment may increase the predicted time to pass through the tube, and suggests that our magnetic dipole moment may be incorrect or there was some other significant error present during data collection. Some possible sources of this error include that contact and friction between the magnet and the tube, because the magnet will make contact with the tube as it falls through it. Thus, the friction force will increase the time that it takes for the magnet to pass through the tube. We also note that there could be air resistance as well as timing and other measurement errors. What if the resistivity of the conductor were reduced as close as possible to zero, and how would the dynamics of the falling magnet change? When there is nearly zero resistance, there is a large induced current from Ohm's law, whose current is inversely proportional to the resistance. Current is also directly proportional to the magnetic field, so a larger current would mean a larger magnetic field, which would mean more magnetic force on the loop. The force on the magnet by the loop would then increase by Newton's third law, and hence the magnet falls with less speed and takes longer to exit the tube since the net force decreases. On the other hand, if holes or slots were cut into the tube, this would have the opposite effect on the ring and the currents in our model. The holes would disrupt the continuation of the ring structure of the tube, and which allow for the induced current to flow around the tube as the magnet falls. Thus, if we disrupt this structure, we reduce the induced current, which makes the magnetic force on the loop less and makes the magnetic force on the magnet by the loop less, and hence the magnet falls with greater speed and takes shorter to exit the tube since the net force increases.